Now we will introduce the idea of hypothesis test for a population mean. In this module, we'll learn to use a sample mean to test a hypothesis about a population mean. We did hypothesis tests in earlier modules. We'll see that the steps and the logic of the hypothesis test for a population mean are the same. As a reminder, here are the general steps in the process of hypothesis testing. Step 1, determine the hypotheses. We've seen this before. The hypotheses come from the research question. There should always be a question. In this module, the hypotheses involve a population mean mu. The null hypothesis says that the population mean equals a number. So remember, we use this h sub 0 to mean the null hypothesis, that mu, the current mu, is the same as what we thought it was before. For example, like 10 years ago, this was the mean value of some data. We're assuming that it's still the same. That would be basically the null hypothesis. But the alternative hypothesis would say that it's either greater than that or less than that or not equal to. So the current mu is less than the old mu, or mu sub 0, or the current mu is larger than the old mu sub 0, or just they're not equal. We're not really sure which one's larger, but we're thinking that they're not the same, and we're going to collect data to see if the alternative hypothesis is correct. We select a random sample from the population. The data comes from the sample. We calculate a statistic, in this case a sample mean, to summarize the data. The third step would be, now we're going to assess the evidence after we've collected the data. If we assume that the null hypothesis is true, could the data come from the population described by the null hypothesis? In other words, are sample means more extreme than the observed data, likely large p-values, or unlikely with small p-values? So we're assuming that the null hypothesis is true, kind of like we said in a previous module, innocent until proven guilty. So the null hypothesis, we're assuming it's true, we're assuming that it's telling the truth, it's innocent, until we've proven that if I take a random sample from a population where the null hypothesis is the case, could this random sample actually come from a population where the null hypothesis is still currently the mean? And we're going to test whether it could or not. If it could not, that must mean the null hypothesis is false after all. Use a simulation or a mathematical model to examine the results from random samples selected from the population described by the null hypothesis. If we use a mathematical model, we'll use the t-model if the conditions are met. We talked about that in the previous module. The test statistic is similar to the z-score. So t is the sample mean minus the hypothesized population mean divided by the estimated standard error. And the numerator, you can also call that the observed error divided by the estimated standard error, where the estimated standard error is the standard deviation over the square root of the number of sample numbers, objects or numbers in the sample. Okay, now let's scroll down so we could see more. So we'll use the t statistic with the appropriate degrees of freedom to find the p-value. As before, a hypothesis test can be one-tailed or two-tailed. If the alternative hypothesis involves a less than or a greater than statement, then the p-value is the area in one tail. The left tail for less than, because those are the smaller numbers on the x-axis, a right tail for greater than, because those are the larger numbers on the x-axis. If the inequality is not equal, that symbol there, the test is two-tailed and the p-value is in the area in both tails. And the fourth step would be, now we're going to state our conclusion. We should know by now whether the null hypothesis is still true or whether it's been disproven as false. We can use what we find in the previous step to make a decision. This step requires us to think in the following way. Remember that we assume that the null hypothesis is true. Then one of two outcomes occur. First, it could be that results similar to the actual sample are extremely unlikely. In other words, a very small p-value when the null hypothesis is true. This means that the data from the observed sample do not fit in with the results from random samples selected from the population described by the null hypothesis. In other words, kind of like how we said, proven innocent until proven guilty. You're assuming this person's innocent, but then all these facts about the case come up and you realize, when if all these things are true, these actually happened, this person cannot be innocent, they have to be guilty. So we're assuming the null hypothesis is true, but if we collect data and it seems like, okay, this p-value, the probability is so small, there's no way that this sample came from a population where this null hypothesis is actually the case, so that must not be true. Yeah, in other words, the difference between the observed sample mean and the hypothesized population mean, in other words, the error, is too large to attribute to chance, the expected variability that occurs in random sampling. In this case, it's unlikely that the data came from this population, so we view this as strong evidence against the null hypothesis. We reject the null hypothesis in favor of the alternative hypothesis. That's the one possibility, that we reject the null hypothesis. The other one is that results similar to the actual sample are fairly likely. They're not unusual. Large p-values. That means they could be a little smaller than mu, they could be a little larger than mu, but they're in the realm of possibility. This means that the data fit in with the typical results from random samples selected from the population described by the null hypothesis. In other words, the difference between the observed sample mean and the hypothesized population mean, in other words, the error, is attributed to chance, the expected variability that occurs in random sampling. In this case, we do not have strong enough evidence against the null hypothesis, so we can't reject it in favor of the alternative hypothesis. Now we'll look at significance level. Okay, that's the last part. As before, we can set a significance level prior to running the hypothesis test if we want to have a firm cutoff for defining statistically significant results. So for example, if the p-value is less than or equal to alpha, I think a lot of times we set alpha equal to some decimal number, then we reject the null hypothesis in favor of the alternative hypothesis. Or if the p-value is greater than alpha, we'll fail to reject the null hypothesis. So you should have an alpha already given to you in the beginning of the problem.